Hey, how's it going? This is Will Sutherland doing Lab 3, Black Hole and Orbits. So this lab had two parts. So the first part was to find the average mass of the black hole by solving for the net force that the black hole exerts on an orbiting star. And part two was to find an initial velocity for the spaceship that would allow it to orbit both the planet and the moon, with the hopes of making a figure eight orbit. Excuse me. So the preview of the results, we found the average mass of the black hole was 1.38937 times e to the 34th kilograms, and the initial velocity of the spaceship was just that. I'm not going to go through all that number. So system, surroundings, initial conditions. System was our star, and the surroundings for part one, the system was the star, and the surroundings were the black hole and just space. And so we know that only the force of gravity, Fg, is actually acting on this, and so which is why I initialized gravitational constant. I also initialized n and total, which we're going to use to find the average value of the mass of the black hole in our code. So part one, so basically components of the net force was what this was about. So and Newton's second law. So Newton's second law is just F net is equal to dp over dt. We know momentum is just mass times velocity, and the force of gravity is just the gravitational constant g times the mass of the system times the mass of whatever is acting that force on the system, divided by r squared times r hat. And again, so this is about components. So we can actually split dp over dt and thus F net into their parallel and perpendicular components. So basically, F net parallel points in or opposite to the direction of the momentum of the object and is responsible for whether the object is slowing down or speeding up. F net parallel is also just shown here as magnitude of final momentum minus magnitude of initial momentum over the change of time times p hat, which is just the direction. And so F net perpendicular points in or opposite to the direction, or to the center of the kissing circle of the object. So n hat, direction of n hat or negative n hat. In our case, it is pointing from the star to the center of the black hole. And so this changes the direction of F net. And F net perpendicular is just mass times velocity squared divided by r times n hat. Oops, sorry. And also F net is equal to just F net perpendicular plus F net parallel. So as you can see here, we did exactly that, found F net and dp dt and both their perpendicular and parallel components, and used those to then find the mass of the black hole at that F net at that time step interval. And so, because of that, that means there is a ton of different masses of the black holes that are actually calculated and printed. So we needed to find the average of all of those. So I just put in n equals n plus 1, and total equals total plus the mass of the black hole. And then you can literally, so where n is just the total number of times the loop occurs, and the total should just be the total mass of all of those masses that are calculated. And then outside of the loop, I then was able to just put average mass of black hole equals total divided by n. And oh yeah, F net perp is just equal to F net minus F net parallel because of what I showed you before, which we were able to do here. So part one, discussion of results. After running the code, the average mass of the black hole was calculated to be 1.38937 times e to the 34th kilograms. And so the what if, as Newton's second law states, the rate of change of momentum is equal to the net force applied to a system, and the parallel and perpendicular components of the rate of change of momentum and F net are equal. However, this does not mean they are completely identical. By definition, the rate of change of momentum of an object only examines the system's change in mass and velocity over a change in time. On the other hand, the net force is the sum of all forces acting on that system. So therefore, the net force is really the cause of the rate of change in momentum of the system. They're not the same. So this leads to part two, where we were trying to find the initial velocity of a spaceship so that it would orbit both a moon and a planet. So in this, we actually had two different systems. So system one was the spaceship with surroundings of the moon and the planet, and system two was the moon with the surroundings of the spaceship and the planet. And we assume that the planet is stationary and there are no other outside forces acting on the system. And this just shows all of the initial masses and everything. And Tmax is 700 hours. So again, Fnet is equal to mass times acceleration, which is equal to dp over dt, Newton's second law. We needed to calculate the net force on each system in order to update each system's velocity and position for each time step. And so again, fundamental force was only gravity, so that's just that. And our velocity and position update, velocity update is just a rearrangement of this Newton's second law. And we know V average for non-constant forces is equal to VF, so we can plug VF into our formula for position update. So the code shows exactly that. This is Fnet of the planet on the moon and Fnet of the ship on the moon. Add those together, gives you Fnet on the moon. Same thing, force of the planet on the ship plus the force of the moon on the ship is equal to Fnet on the ship. And this is just showing applying Newton's second law. So the velocity update and the position update for the moon and the ship respectively. So as you can see here, this is our, here I could speed this up actually. So in cyan, that is our moon orbiting the planet in blue, and magenta is our spaceship. And so right now it is just orbiting the planet, not the moon, until here, boom, right there. Now it is orbiting both systems, just like that. So it's pretty cool. But yeah. So part 2, discussion results. After much trial and error, using an initial velocity of negative 19,750.20797 meters per second in the x direction and 31,980.01044 meters per second in the y direction, produced a simulation where the spaceship orbited both the moon and the planet separately, as you just saw. However, I was unable to produce a figure-8 orbit because that's just really hard to do. So the what if is, if we wanted to predict the motion of the entire system, the moon, the spaceship, and the planet, we would need to also find the net force acting on the planet by the force of gravity on the moon and of the spaceship, and use it to then update the planet's velocity and position, just like how we did in our code before for the moon and the spaceship. So this would cause the total system to have motion, not just the spaceship or the moon. And however, this motion would be pretty close to zero, like it is right now, since the planet is just much more massive than the spaceship and the moon. So, in conclusion, overall, this lab strengthened our understanding of orbits and the changing forces of gravity between multiple systems. And we also practiced finding and relating the parallel and perpendicular components of the rate of change and momentum of a system and the net force on that system. So, thank you very much.